Good evening from Highlands Astronomical Society. My name is Eric Walker, and I am chair of Highlands Astronomical Society. Welcome to all our sister clubs, and welcome to all our new members and all our guests. We've got some first-time members who have contacted us wanting to find out what we get up to, and I'm sure you're not going to be disappointed. You may have noticed I'm a wee bit more excited than usual, and that's not just because we have two excellent presentations coming up. It's more that this is the first Zoom webinar we are operating ourselves, and there is a team of us in the background who are getting our acts together to successfully deliver you tonight's programme. The timings tonight are after my initial welcome. We'll have our main talk, followed by a question and answer session. Then about 8:30 or so, we'll have our club news and Astropics for the month, presented by Pauline. And then I will wrap up the meeting, take us to the close about 9:15. After this meeting, there will be a post-meeting Zoom blether again. The link will be provided in the chat box near the end, and it's also in the email that you received from Rona notifying you of tonight's events. As usual, there won't be any breaks during the meeting, so if you need to leave for any reason, just get up and go, but keep yourself connected to the meeting. If you've any questions for the speaker, please put them into the Q&A section at any time throughout the meeting. If you've got any problems, click the hand icon and someone will get in touch with you directly via chat. The chat for the general chit chat is going to be switched off during the main part of the meeting to minimize distractions, and also some devices. It takes up quite a bit of the screen, so we're going to switch that off for a while, but it will be switched back on near the end. So last month we held our AGM, and I'd like to thank all the members who confirmed by email that they had received all the AGM documents and made the effort to submit constructive suggestions and comments for us, your committee, to consider. We are now able to prove to the Scottish Charities Regulator, Oscar, that we achieved the required AGM quorum and can now submit all the documents, financial report, and this year's operating plan, which we are legally obliged to do. So, what have we been getting up to? Well, the weather was very good for the first 3 weeks of April, and we've seen lots of observing activity from our own and affiliated club members. Beautiful photographs of the Northern Lights, the moon, the last of the deep sky astrophotographs. There's no more proper astronomical night from now until the end of August. We've also got pictures of constellations, asterisms, the Milky Way, and now the sun, which is bursting into activity at the early stages of solar cycle 25. Pauline has a bucket load of our images to show you later. WhatsApp has been very active when there are things to view. The Nebulous News group, it works especially well alerting members to something that is currently visible and photographable, if that's a word. The All Sky camera has produced some beautiful star trails and time-lapse sequences, some of which you'll see tonight. No noctilucent clouds yet, though. We'll just have to wait a wee while for those. And so, back to tonight's meeting. I'm going to introduce our main speaker for tonight, Professor Jane Greaves. Jane is a radio astronomer with a PhD from London, University of London, working since then in the United States, Scotland, and now Wales at Cardiff University. She's interested in all aspects of where the planets come from and the possibilities for life beyond the Earth. She describes herself as a dabbler in the science, sci-fi, crafting interface. And tonight, we have to look out for accidental appearances of a knitted Dalek on our webinar, and I think I can see it just now. Jane's talk tonight has generated much interest across our North of Scotland amateur astronomy community, and we have several first-time visitors attending to hear her firsthand. I'm particularly excited by the synopsis of her talk, which says, Carl Sagan was one of the first to suggest that the high clouds of Venus could have offered a refuge for microscopic life when the planet's surface became scorchingly hot in the distant past. Jane's team studied this idea using radio telescopes to look for a gas that any such floating life forms might emit. And they found it. Without further ado, I welcome Professor Jane Greaves and her talk for tonight, Strange Gases on Venus. Over to you, Jane.
Thank you very much, Eric. And thank you also for volunteering to show the slides for me, as I've got a bit of a slow computer at this end. Okay, so I hope that's visible for everyone, and that you can see me as a tiny postage stamp, as my mother would say, and also hear me all right. And the technical support have been great so far, in case anybody has any problems. Okay, so strange gases on Venus. I'll introduce you to what our team did and what we discovered and some of the implications, and then I'll try not to run on too long because I'm really looking forward to your questions as well. So if we could go on to the next slide, please. So it's very exciting to think about the prospects of life beyond our own Earth. And as modern day thinkers and astrobiologists, as I suppose this career could be called, we first look at the Earth to see some of the extreme conditions that life exists here, to give us some ideas of how perhaps conditions that life could survive or even emerge under on other planets. So we have to think really about some kind of life with properties that we'd recognize. And also, there's a whole suite of effort going into looking for life signs from extrasolar planets, planets outside the solar system, but I won't have time to touch on that topic tonight, so I'll just talk about the solar system itself. So I think this field really got going with studies of exotic habitats on the Earth in the 70s and 80s. So submarines visiting the deep sea floor, for example, and this is a shot of black smokers, which indeed are a habitat on the seafloor. So apart from the lights of the submarine, it's completely dark down there normally. So the source of energy for life is actually the heat inside the Earth. It's not sunlight at all. So it's quite a different basis to what we're used to thinking about with plants and animals and so on. And I think that's really guiding our thinking in the search for life off Earth. So we're not expecting perhaps to find some advanced creature waving hello to us. We might from another planet, but probably a lot more habitats, like a lot of the time for the history of the Earth, really only hosted small organisms, but sophisticated ones very well adapted to their environment. So these seafloor habitats have indeed a lot of microbial activity, and indeed going up to quite large life forms in that case. So let's think about the rest of the solar system. If we could have the next slide. Thank you. Okay, so I'll just contrast here two of the cold kind of habitats we've thought about. And we've got pictures here of Jupiter's moon, Europa, and also a picture of Mars. So looking at the crater on Mars in the middle of the frame to start with, that's water ice on the surface. And we know there is water on Mars, but it's so cold and the air is so thin that it's really frozen water. These days, in modern times, it's not running rivers on the surface, but those may have existed in the past. So if in that more clement past, life originated on Mars, there might be some relics of it possibly below the surface. So if we can send enough landers and diggers and perhaps even people to get a few meters down, we might find some strange microbial life still there today. Or we certainly might find some kind of fossilized, mats of algae or something that would indicate life was there in the past. The search of solar system moons is also very exciting. So Europa is one example, and the diagram is just showing you how much water you'd get if you took all the oceans of the Earth and put it into a kind of giant water marble, compared to how much you'd get from Europa. And Europa actually hosts more water than the Earth, but it's hidden between the thick ice shell, which is kilometers or tens of kilometers thick above it. But in a way, that's a bit like the deep sea habitat we just looked at. If there are energy sources inside, trapped heat inside the moon, there could equally be black smokers or something like that on essentially the sea floor or the lake floor of moons like Europa. So the moon is much smaller than a planet like the Earth, but possibly some life could have got there or even started there. Okay, so let's go on the next slide, my main topic tonight. Surely Venus is a stupid place to think about in the context of life. So probably hundreds of millions of years ago, or even billions of years ago, when the sun was a bit less luminous than it is today, the surface there could have been quite nice. We have very little visual evidence, but there might also have been oceans and continents there. And the reason we have very little visual evidence is very few landers have made it, and none have lasted more than an hour. But through heroic efforts, they have sent us back data. And indeed, some of the imagery that was compiled here for this composite photo, which unfortunately I don't have the author of the composite, but I know this is a color matched and stitched together version of the view from one of the Soviet Venera landers back in the early 80s. So it looks pretty harsh and rocky and dry. The main problems with the surface of Venus are the pressure these days is something like 90 times what it is at the surface of the Earth, and the temperature is hundreds of degrees centigrade. So the landers would have just stopped working because sensitive electronics would have started to melt and so on. So although in terms of gravity and things like that, Venus is kind of a twin planet to the Earth, something went very wrong with the climate there. And probably as the sun warmed up, the water started to evaporate if there were any oceans and became a great insulating layer. And you've now got a dry carbon dioxide atmosphere today under enormous pressure. So really, we can't imagine any life there today. But on the other hand, the clouds of Venus, my main topic, are quite different to that. So if we go to the next slide. Okay, so the diagram on the right is talking about the so-called habitable zone of Venus. And this indeed is the suggestion that goes back to the 1960s of Carl Sagan and some other scientists then. So they thought that as the surface of Venus became uninhabitable, which probably took hundreds of millions of years, it wouldn't have been an overnight event, some small microbial-like life might be able to detach itself from the surface and gradually sustain itself in the atmosphere and eventually end up in a layer that today is what we would call temperate. So this will be free floating life, a biosphere, just meaning an occupied sort of habitat with small organisms. So they can't be anything large or they would plummet to the surface, but things of microbe-like size ought to be able to live up there. And this is thought of as a temperate zone because at about 50 kilometers up, which is about 5 times higher than the top of the Earth's atmosphere, say, in these very high clouds, the temperature is, I don't know, 20 centigrade, maybe on average, and the pressure is up to about 1 bar, the pressure at the surface of the Earth, hence the name, the temperate zone. On the other hand, it's really not a nice place. As we think of it, you can see from the diagram, the wind speeds are extremely high and the clouds there are heavily made of sulfuric acid rather than water, a topic I'll get back to. So does this aerial biosphere idea have any reality at all? Yes, we know that it does because Earth has an aerial biosphere, although in cool, wet conditions, rather different to those on Venus. So I don't know how well the diagram on the bottom left came out, but it's essentially showing you a water droplet in Earth's clouds and how microbes can operate inside. So the various processes needed for an organism to reproduce are all possible inside the droplet, and gases and liquids are exchanged with the surroundings. So it's not a massive amount of life on Earth that occupies this habitat because the surface on Earth is so much nicer. But we do know these little creatures are there, and indeed they seem to reproduce at altitude. They don't have to, for example, settle to the surface for some parts of their life cycle. And that's important for Venus because nothing could settle to the surface without being completely baked and crushed. Okay, so the next slide. Thanks. So one of the main things, as I mentioned, about Venus is the extremely acidic conditions. And we do have acid conditions on Earth that we can think of as a bit of a template. So the picture here is showing you the hot springs, which are near the summit of an old volcano in Ethiopia. And the colors are actually from heat-loving organisms, as you might see in some of the exotic national parks in America, for example. But this Ethiopia example, the heat-loving organisms are also acid-loving, so they're acidophiles, small acid-tolerating creatures. And if you remember your school chemistry at all, or perhaps you're still doing chemistry in school, and you think of your litmus test, the acid scale goes down to a pH of about 1. And that's kind of like the conditions 1 or even 0 in these hot springs, where it really is a few % of acid in the water, and yet the creatures have adapted to survive there. And that's a point I will come back to for Venus later on. Okay, so we've set the scene a bit. Let's go to what my team did. If we look at the next slide, thank you. So it would be great to send more probes to Venus. You know, maybe a balloon that could float in the clouds, lots of instruments, sample, take images, and so on. But before that happens, our best bet is really to use the telescopes we have on Earth, and we can particularly look at the spectra we get from the atmosphere of Venus, which tells us what gases are there. And this is something you can in fact do with your own amateur telescopes you may have at home or that the society may have. So if you put a diffraction grating on the front of the lens or between the telescope and the camera, you can spread the light out as shown in this simple attachment here and get a rainbow of light. So all the different wavelengths, i.e. all the colors of light. And what we can do with modern telescopes is we can do this equally well with longer wavelengths that the eye doesn't see. So infrared wavelengths or even radio telescopes, though with radio technology, it's done more electronically rather than literally a filter. But this is how we discovered some interesting gases in the atmospheres of the gas giant planets. So we're now talking observations in the 80s and 90s. And what you're looking at is one of these spectrums shown as a graph rather than as a color image. So as you go along from left to right, you're looking at shorter to longer wavelengths. And what we're looking for at a particular wavelength is one of these V-shaped dips where you lose a bit of the light of the planet, in the infrared in this case, because the molecules in the atmosphere, the gas molecules, are absorbing that light at a particular wavelength that they resonate or vibrate at, or some such physical process. So you've probably spotted on there NH3, which is the chemical formula for ammonia. And also what I like to think of as its kind of heavy metal twin or evil cousin, PH3. So ammonia is a nitrogen atom with a kind of 3 legs of hydrogen atoms sticking off it. And phosphine is an even more toxic version of the same thing with a heavier phosphorus atom and 3 hydrogens hanging off it. And the gas giant planets, Jupiter and Saturn, are mostly made up of hydrogen. So this is kind of a natural thing to find there, where the conditions of temperature and pressure are right. You can, if there's any phosphorus available, you can easily form phosphine. Okay, so if we go on to the next slide, now we know what phosphine is. Why is it interesting? So my idea was to look for phosphine in the spectra of the planet Venus, where it would not be an expected product. Okay, so Venus is what we'd call an oxidized planet, same as the Earth, really, where oxygen chemistry and oxygen compounds dominate conditions at the surface and in the atmosphere, and there isn't a whole load of free hydrogen atoms to make hydrogen-based molecules. Okay, so you wouldn't naturally expect phosphine on Venus, and also you wouldn't naturally expect it just as a chemical product on the Earth. So on the Earth, it's sometimes made. It can be part of manufacturing processes, or indeed, I think some drug-making processes of the illegal kind tend to produce phosphine as well. But there's a biological source, which is where there are anaerobic tiny organisms, so anaerobic bacteria. So if you sample in some kind of swamps that are low on oxygen, for example, you find phosphine. Also, the bit that really entertained me about this is apparently the insides of penguins are a great anaerobic habitat for bacteria. So you can be a penguin scientist that follows them around, tracking the waste products and seeing how much phosphine they put out, which I don't know, tells you how healthy the penguins are or where they've been or something. So there's a nice picture of a genuine Gentoo penguin, the kind that's taken part in this kind of study. Okay, so we I get a lot of jokes about this, but we are not looking for flying penguins in the clouds of Venus, but we were thinking there might be some of these anaerobic bacteria which are capable of putting out phosphine, and phosphine is not naturally made on Venus by other processes. Okay, so the next slide. Okay, so this is the telescope I went and asked if they would get us some of this data. This is a radio telescope, so it's the James Clerk Maxwell telescope, which is on a high dry mountain site in the islands of Hawaii. You can see it here inside its dome. This is a very wide angle view standing in front of it. So it's a lot of metal panels sending the light up to the smaller secondary mirror at the top and then through the hole to the instruments behind. And the instruments are pretty much electronics cooled down with liquid gases. So the picture on the left, the small blue cryostat is where all the action takes place, and you've got all the readouts around it. And then just for a bit of scale, that's the actual instrument we use, the blue one. And there's the deputy director of the telescope and the director of operations, my friend Jess Dempsey, who is actually the one who approved us to use up to about 8 hours of this valuable telescope time to do our observations. Okay, so what did we do? Let's have the next slide. We looked for one of these graphs of the spectrum, look like the ones we just saw of Jupiter and Saturn. So I had this idea now about 5 years ago. It took a while to get onto the telescope and get everything up and running. So when Venus was a morning object in 2017, they took this data for us. And it looked really complicated. They actually got us 140 separate spectra, all of which had their own problems and scruffy nature. So what we're looking at here at the left and right of the diagram, there's just random signals going up and down rather than being zero, and those don't mean anything. But you can see the V-shaped dip in the center just faintly is sticking down more than the random signals. And it wasn't exactly the right wavelength to be phosphine. So we can take that wavelength, which you may remember, sound and light waves can be stretched or compressed if they're coming from a moving source. And we can turn that stretching or compressing of the wavelengths into a measure of how fast the source is moving. And that turned out to exactly match the velocity of Venus. So we really thought we were onto something. And my colleague Hideo Sagawa in Kyoto Sangyo University in Japan, who's an expert on Venus, ran a computer model for us, which we then processed in the way that we'd had to process the data, went through a lot of complicated steps, but came out with that solid red line, which really matches over the data nicely. So it's not a super strong signal, but to my astonishment, we thought we really had detected the phosphine. And I thought we'd just get some kind of limit on this. When we started this, it was worth a few hours of time, and we could say, maybe we could rule out some hypotheses and it would take us a little further on. But we did actually get this detection. And so we thought, this is so exciting, we need to make sure maybe another telescope could do this as well. Now, phosphine has a series of these wavelengths at which it absorbs, but most of them don't make it through the Earth's atmosphere. And so we had to look at the same wavelength again, but we could go to other telescopes. So if we go to the next slide, the director of the Atacama Large Millimeter Submillimeter Array, or ALMA for short, kindly agreed we could use another 3 hours or so there on the huge network of telescopes on this international facility. So these are almost as big as the James Clerk Maxwell Telescope, which is a 15-meter diameter. These are 12-meter diameter dishes, and we used, I think, 43 of them, all pointing at Venus, trying to do our project. And they're normally looking for faint galaxies and black holes and all kinds of difficult things to do. In fact, you can see the Large Magellanic Cloud in the background of this shot. That's quite a difficult galaxy to study, although quite near to us in our own part of the universe. But they're more used to doing that kind of thing and trying to do really bright planets, our closest neighbor planet, but look for a very faint absorption V in the spectrum was actually really hard. But that's what ALMA did for us. So if we go to the next slide, this is what we got. So let me talk you through. So basically they again found the phosphine. So this is the spectrum shown as the blue at the bottom part of the diagram, and you can see that V-shaped dip, and there's overlaid on it a blue dotted line, which is again the computer model, and you can see it really looks like it should. And we also were able to check for some other molecules in the atmosphere just to make sure all the technology was working as it should. So there is a wavelength quite nearby where a much more common molecule, sulfur dioxide, also absorbs, and that's represented by the little red line in the bottom part of the diagram. But you can see that's nothing like as deep. So it wasn't like we detected sulfur dioxide. We really have detected phosphine and maybe a bit of sulfur dioxide as well. And then the top part of the diagram, and that's not really meant to be up there, it's just I didn't want to put all the lines on top of each other. Other molecules that are known to be there include small amounts of water in the clouds of Venus. Now, ALMA would struggle to look for plain water because it would tend to detect the water in the Earth's atmosphere, but it can look at a different wavelength for a kind of heavy water where one of the two hydrogen atoms has been taken out and replaced by a heavy hydrogen or deuterium atom, and that gives you deuterated water. The chemical formula for which is HDO. And that, again, we've got a computer model overlaid on top, and you can see it really looks like it should. So yeah, left and right of the diagram, scruffy things that are just noise, scatter in the observations, but we've really got the absorption lines. So the two gases, HDO and phosphine, PH3, really are there in Venus atmosphere. So that was a huge amount of work, and it wasn't just the team that I brought together for this, but observatory specialists who normally do other things, people from other science teams around the world, all played vital roles in this. Anyway, that was pretty amazing. So let's go on to the next slide. Okay. So we published our results back in September, and you got a lot of feedback, but some other people were really excited as well. And a team in America led by a guy called Rakesh Moghul realized that he had access to some really old NASA data of Venus that might be relevant. So NASA's sent a lot more probes to Mars than it has to Venus, but very early on they sent the Pioneer Venus mission back in, we're now talking 1978, and that descended through the clouds and captured some of the gas molecules in the atmosphere and measured their masses. So it wasn't a telescope and a spectrometer on board, it was literally a kind of chamber that measured the masses of different molecules there. And all that was published at the time, or in about 1980, with the major components of the atmosphere, and they got great results. But Rakesh went back after seeing what we got to see if there were some weaker signals there from rarer molecules. And his team found that they had discovered phosphine kind of retrospectively as well. And they're pretty sure of this because they called in one of the guys who worked on the original mission. So more than 30 years later, one of the technical staff looked at the data again and is helping them. This is somebody who built the instrument, so they really know what they're doing. And I'm not sure if Richard Hodges came out of retirement or was still working, but anyway, he put his head together with Rakesh Mogul and their team. And in the diagram, and I won't really bother too much about what the X and Y axes of the diagram are, but the red curve is showing you they detected something with the mass of phosphine. And so we know the probe went down through the clouds. They measured the altitude at which they detected it. So they've got phosphine very much in the heart of the temperate zone, about 50 kilometers up. So that was astonishing. Okay, so if we go on to the next slide. We've put a lot of thought into where could the phosphine come from. So this really was a search motivated by the idea of looking for life, but we can't just dance around going, we found life. So we've gone back and looked really hard for what you might call natural chemical sources or natural geological sources. So I mentioned there isn't free hydrogen in Venus atmosphere, so we were unable to find any chemical routes that would just make phosphine by some reaction between other gases, or I don't know, some weathering at the surface or something like that, because there just isn't enough hydrogen around for this to work spontaneously, however you calculate. But there could be maybe some other source, something pumping phosphine into the atmosphere. And one of the things that's been suggested is volcanoes. So the hot surface of Venus, excuse me, probably has lots of volcanoes today, although they're largely hidden from us because of the cloud-covered nature of the planet. But these are shots from a couple of orbiters. So the top one with radar, they found something that looks very much like a volcanic shaped mountain. And then the false color one at the bottom is actually a map of the heat coming out. And it also looks like a hot spot, like it could be a hot volcano. And indeed, one of the orbiters was lucky enough to catch a hot spot that appeared and then went away again. And that was very likely a massive lava flow from an active volcano, which then cooled. And so it just turned into kind of background rock and they didn't see it again. So we're pretty sure there's volcanoes there. And phosphine is something, phosphine gas is something you could make in the plume from a volcano. So we looked at that. It's not terribly likely to be the solution because we think it happens, phosphine is made in volcanic plumes on Earth, though that's pretty difficult to sample. I don't know whether you send a drone through or something, but it's a difficult, obviously an difficult experiment to do in the middle of an active eruption. But we think the phosphine is part of a chemical network there that includes water, because you can have water in volcanic plumes. And on Venus, there just isn't the water, and so it's also probably not the phosphine. But it is a possibility. But one point I also want to make on the back of this is it'd have to be an active eruption now. You couldn't have had a volcano go off thousands or millions of years ago, because all the gas molecules are carried up by air currents, and phosphine, once it got really high up, 80 kilometers or so, would just be destroyed by sunlight. So you do need something actively making the phosphine right now. Okay, so that takes us on to the next slide. Okay, we did look quite hard about whether this idea about life making phosphine in the conditions of the clouds of Venus is crazy. And at this point, I think I thought there's going to be some complete showstopper. You know, the original idea would have been wrong completely, and I would feel a bit silly. But that's not turned out to be the case. So we could measure how much phosphine we were detecting with the telescopes. And it's very scarce. It's a few molecules of phosphine for every billion of the main gas, carbon dioxide. But it is definitely there. It's just a small trace. But that sort of quantities is, in fact, what microbes on Earth make. They pump out production rates at about the same amount that would be needed on Venus to end up with a few parts per billion that we saw. So that's not crazy if there could be organisms on Venus working in a similar kind of way. And then my very clever colleague, William Baines, thought about that diagram we had near the beginning of the droplets with the microbes inside them and did something similar for Venus. So that's the diagram at the top, labeled with some chemical reactions that will be sources of energy and so on for the cell, which is drawn as a kind of blue rectangle inside the larger oval, which is the cloud droplet. And through this chemical pathway, you could have something living, and it would indeed put out phosphine gas, which is the arrow on the right side. The thing to note is that the droplet in this case is largely sulfuric acid and a pH of about 0, whether we're thinking the cell inside has got to be something like a neutral chemical on Earth with a pH of about 7. Okay, so maintaining that difference is a huge issue. Another thing is, well, would your organism be able to float? And so my colleague, Professor Sarah Sagan, and her team at Massachusetts Institute of Technology worked really hard on this. And they reckon that things could probably exist solely in the clouds. So they would go around in a kind of cycle like you see in the lower diagram. So they'd be in these droplets, they'd be reproducing, putting out gas and so on, eventually cycle down a lot of them to a lower layer. Some of them might fall out and end up being destroyed lower down. But the ones that got kind of carried along and then up again, their droplet would probably evaporate, but they could go into a kind of desiccated spore phase, which is what organisms do when conditions get too harsh on Earth. And then if they were carried up again, they'd be like a nucleus for a new raindrop in the clouds on Earth, and the whole cycle could go round again. So it does look theoretically possible that you could have an aerial life form that really needed no contact and wouldn't indeed survive any contact lower down with the very hot surface. The thing we tried to emphasize all along is there's an awful lot more work needed to be done in these very strange conditions on Venus to see if the idea of life is actually not crazy. So I mentioned the droplets, acid and water, but they're mostly acid rather than being mostly water like any habitat would be on Earth. So my colleague Paul Rimmer at Cambridge University in the Earth Sciences department there has done some work on this very recently to see just how acid it is, taking into account other things we know about the chemistry of the clouds. And he reckons in his computer models that the pH might not be completely acid. We were into like negative pH territory with the scale at some point because you were talking about sulfuric acid in water. We were talking about water dissolved in sulfuric acid, essentially the wrong way around. He now reckons the pH might be only, so to speak, about 1, and that is quite like the Dalol hot springs I mentioned at the beginning, where life does survive even though there is quite a few percentage of acid in the water. So it's still kind of a crazy idea, but we haven't really found too much of another explanation. The volcanoes thing didn't really work out. We're waiting on a lot of other people to come up with other ideas, but the life explanation is still viable and still worth thinking about, which is an astonishing outcome compared with a little project I kind of scribbled down in the back of a meeting 5 years ago. Okay, so I think I'm nearly at the end because I wanted to leave lots of time for your questions. So the next slide is what will we do next, I think. Yes, okay. So we're really hoping that the telescopes will let us have another go at this so we can get more detail. It is very difficult for these telescopes that are in remote parts of the world. So ALMA's quite struggling. I'm very sorry for them with the COVID situation in Chile, which is not very under control. So even things like staff sharing a jeep to get up on the plateau to see what's wrong with the electronics on a telescope is not very safe at the moment. But they are operating, and so we're hoping that as things improve, they'll allow us to use ALMA again. And similarly in Hawaii, and they've got some exciting new instrumentation there, and they're a bit closer to their telescope and they can work it robotically without putting people in danger. So we're really hoping to get to use both of those again. Particularly ALMA could give us more detailed images. I've just shown you these pointy V-shaped things, which are spectra, but we could get those for different spots on the planet and try and tie them into other data. So the picture you're looking at there is from the Japanese JAXA-operated spacecraft Akatsuki, which is taking images of Venus in lots of wavelengths, including the ultraviolet. And one thing they're very excited about is they see in ultraviolet images these dark kind of streaks and clouds that come and go. And there is a bit of a hypothesis that these could be something like the microbial colonies on a very large scale. And maybe, you know, bits die off or bits evolve, or they're swept around by the winds or something like that. And so the shapes form and break up. So if we could get data that tied in with that, that would be extremely exciting. We also need to think biologically. How do aerial biospheres work? The idea that organisms can reproduce in the Earth's upper atmosphere has only been accepted, I think, for a couple of years. So it'd be lovely to do some experiments on that. I have a sketch of that in the bottom, which my colleagues are firmly telling me will not work. That's basically me holding a microbe under a hairdryer blast and seeing if it adapts to a free-floating life form, lifestyle. Be told that won't work. So I'm waiting for my colleagues to come up with something slightly more sophisticated and expensive than that we can try at the university, hopefully. But particularly we're hoping that there will be new missions to Venus. As I've mentioned, the missions, most of the data came from the 70s and 80s, and it's a huge and valuable heritage of actually going there, of sampling missions. But we could do so much more with new missions. And I'm not saying, you know, it's not take our attention away from Mars, but I'm saying, you know, let's pay a little bit more attention to Venus. So the next slide just gives a bit of a hopeful timeline for this. Okay, so several space agencies had already expressed an interest. This wasn't to do with our work, they were already keen anyway. So the first is Rocket Labs, which is a New Zealand-based private space agency. They mostly launch small satellites into low Earth orbit, but they do have a powerful rocket that they can do what they like with. And so they're really interested in making one of their first interplanetary attempts to launch a really small probe down through the clouds of Venus again. And that might even be in a couple of years' time. There's a launch window then. NASA have on the drawing board another mission, which as shown would descend by balloon, have lots of instruments scanning and imaging there. That's in competition with other things for about a 2026 launch slot. And then a really big mission, there's a European Space Agency project called Envision, absolutely packed with instruments that would study with radar the topography, the volcanoes on Venus, the ancient continents, the atmosphere, how it all works. And that is up against one other candidate for a 2032 launch slot. So I think there's some really exciting opportunities there, ranging from next couple of years out to about a decade out or so on. So particularly if we've got younger scientists in the audience, people perhaps doing science degrees, this might be something really great to hook your career onto later. And indeed, of course, for older scientists, remembering the guy who worked on Pioneer Venus, who still knows it all 40 years on and got that amazing result from that probe. I think I'll just go to my last slide, if I may. I just wanted to show you the team, to show you we're not a faceless bunch of people. This is my entire science team, many of whom came together for this Venus project, and indeed quite a lot of whom, with the circumstances, I have never actually met, but they're all lovely people from various countries and various different branches of science. And so I wanted to show you who works on this and the diversity of our team and how well they came together, people who didn't know each other before, but just in the interests of science. So I think that's me. We could perhaps go back one slide, have those nice images of the future space missions, and I will leave it there as far as me talking, but I'm very much looking forward to your questions. Thank you.
Well, thank you very much, Jane. I've got quite a few questions.
Brilliant.
I'm a bit puzzled about the wind. This is my question. You said that there's very strong winds on Venus. Are they much stronger than those on Earth?
Yes, so there's a global wind pattern. So although the planet itself rotates very slowly, these super winds, as they're called, would carry something around the planet in only about 4 or 5 Earth days, which is something we don't have on Earth, as I understand it. So probably like a steady wind. So if you were a microbe, you might not even notice you're being carried along. But they suddenly noticed it when they sent some of the probes. So I read somewhere in passing, they mentioned that one of the Soviet probes landed 13,000 kilometers away, latitudinally, sideways, from the point where it entered the atmosphere. And it was meant to do that. It went down slowly, but that's how far it went, you know, about a third of the way around the planet before it actually reached a landing point.
Oh, I think you've answered my next question, because I was trying to work out how, if you were a little microbe zipping around the atmosphere of Venus, how nice that would be for it. But you said you probably wouldn't notice.
I think if it was a steady wind rather than a really sort of turbulent wind, I think you wouldn't notice. You know, if microbes on Earth can survive bubbling up and down in hot springs, I think the wind might be the least of its problems on Venus.
Okay. There's a question from Sam Robinson. It has been suggested by a team in University of Washington that it is sulfur dioxide that was detected, not phosphine.
Yes, so this came up quite a lot, but we had actually looked at it already at the time when we put our publication out in September. So there is sulfur dioxide absorption, but it's not very strong at this particular wavelength. It's not one of its like really strongly absorbing quantum transitions of the molecule. And so we, provided we have data at more or less the same time of some of the stronger transitions, we can make a kind of computer transfer to how much absorption it would have produced near the wavelength of that we're interested in for phosphine. And we do actually have that simultaneous data. So I think some of the people who've said it must be sulfur dioxide, which on the face of it seems like a perfectly sensible explanation. They were not so familiar with some of the technical details and the way we'd use to rule that out. It's a very complicated thing to observe and interpret, but the key is to have this simultaneous observation.
Okay, thank you. Now, the Nicholsons from Caithness have asked, atmospheric geochemistry on Earth includes reactions catalyzed on the surface on materials, clays especially. Is this a viable option for atmospheric phosphine with H scooped from hydrated minerals?
Yes, so this is something we've tried to think about. So you can imagine, say, bits of grit blown up from the surface or something, providing a tiny surface for chemical reactions. And as you say, catalysis to speed these reactions up. And this might turn out to be an explanation. The main issue is our lack of information. So there wasn't a kind of grit catcher on any of these descent probes. So we really don't know what the solid particles in the atmosphere might be like, anything about their composition or size, or we have literally one other measurement of actual phosphorus, which again is one of the Soviet probes managed to measure an abundance of some kind of phosphorus, but they don't even know if it was a liquid or a solid or what in their 1980s measurement. So it's another kind of sanity check point for us. So we've done most of the calculations on the idea that how much phosphorus bearing stuff could there be at all. So we look, for example, at meteors, which might be a source of grit into the atmosphere as a meteorite breaks up. But you just can't have enough there. So in principle, if there was some very strongly phosphorus bearing rock on the surface and lots of its grit blew up, then we'd have to do a chemical reaction network for that. At the moment, we're thinking that's probably not an explanation, but we are a bit in a lack of data situation. So yeah, thank you for that really good question. I hope I've answered it in a reasonable way, given I'm not a chemist.
Thank you, Amy. Now there's another probably, well, even more difficult question, I suppose, from David Ray. Would the microbes be a remnant of a more evolved life form, or do they represent as far as life got on Venus?
Yeah, so it's a bit sad to think perhaps there was even a more advanced ecology. You know, if oceans could have persisted, say, for hundreds of millions of years or even longer, it seems there could have been a more advanced ecology and complex life forms. And obviously that's quite a guess, because you think there was the Cambrian explosion on Earth a few hundreds of millions of years ago, where life became larger and complex and had a lot more features. We don't necessarily know exactly why that happened when it did, so we'd be really guessing for Venus. So it could be the microbes are the only survivors of larger and a great variety of life forms. I mean, the microbes would have to be pretty complex things in themselves if they're there. We have done a little bit of thought about what would be the largest thing that could keep flying. And somebody suggested that tardigrades, which are almost visible to the naked eye, which are these tiny water bear things that you see pictures of, might actually be light enough to float.
And they
not
can survive.
quite as large as the one in Star Trek Discovery Series 1, where it was guiding the starship, unfortunately, but perhaps something almost visible.
And they can survive anything, can't they?
Yes, so they can survive being dried out and, you know, hit with lots of radiation, and you know, they've scraped a few off space stations like Mir and the International Space Station over the years and brought them back inside, and they're like, okay, everything's good, here we go again.
Right, there's another question. You might expect hydrogen sulfide or methane to be co-products in an anaerobic type of metabolism. Is there evidence of this?
Yes, so methane has been looked for. I'm not sure about hydrogen sulfide. That's a nice suggestion, actually. I will look into that. So methane was a huge biosignature gas for probably a couple of billion years on Earth before oxygen came along. So when Earth was anaerobic, methane, if you were an alien looking from far away, would have been the signature to look for. So Rakesh Mergel's team also found some hints of methane, which is CH4, the chemical formula. The niggle with that is that some of the solvents used to clean spacecraft before launch would leave residues, and it's quite likely that methane would be a byproduct burning off of that, a residue burning off as it went down through the atmosphere, as I understand this issue. So the methane and indeed some other chemicals you could detect wouldn't necessarily be to do with the atmosphere. They might just end up in the sampling chamber by chance.
Are there any other products of life that you might look for that haven't been looked for?
Well, yeah, this is the issue, because we're not entirely sure what to look for, because phosphine was such a wonderful example. And my colleague, Dr. Clara Souza Silva, who's also at MIT in the States, has done some thinking about this for extrasolar planets. So she's part of the team there at MIT on something called the All Small Molecules project, where they're trying to identify ones that are really good biosignatures. And the reason phosphine was so great is because it's really hard to make it in any other way. But a lot of the other molecules, unfortunately, can be made in other ways. So methane's a very exciting possibility as found on Mars, possibly from some trapped kind of underground cavern with the gas leaking out. But the gas pocket there might be an ancient volcanic pocket rather than an ancient inhabited area. So methane is a bit of a problem, and a lot of the other chemical compounds are as well. But it is something we're looking into, yeah.
There's a question from Dave really about this. Can you explain how you filter out the noise, I think what you mean is chemicals, from the Earth's atmosphere?
Yes, so the noise we basically get in the signal, where you see that bar chart go up and down, is essentially just random electronic scatter. So if you observe for longer, that should go down. Some of the real problems we had are where you've got something that's kind of halfway between just random noise and an actual signal. like something intermittent. And we had problems with the JCMT, for example, where Venus's radio signal is so bright, it bounces off all the surrounding surfaces, like the floor and the top of the dome, and then it adds itself back into the signal chain, and that causes all sorts of problems. So it produces a peculiar kind of systematic effect. So it's not exactly a noise, but it's like a undulation of the spectrum, which is really undesirable. So we spend a lot of time trying to, well, kind of we could understand where that's from. So if it's a reflection, you can go, oh, that matches how much later it would come in from the floor. That makes sense. But some of these effects that are really unstable, we had to do with things like, we think like cables are flexing, and you can't avoid that because the telescope needs to move to track Venus across the sky. So we went fairly kind of experimental in the end, and we just tried to measure those patterns and subtract them out. So I don't know if that's too much nerdy detail. It did take me a couple of years to do that, so I'm restraining myself with even more nerdy detail.
Well, thank you. And I think this is the last question if nobody else asks one. Colin says, would it be ever possible to terraform Venus, or are conditions well beyond that?
Oh, that's a good one I've not had before. I think the problem is the sheer amount of atmosphere that has built up. So I don't know, when you think about CO2 capture we try and do on the Earth, you know, to help climate change on the Earth, that's obviously pretty difficult because of the large amounts of CO2. And on Earth, it's largely carried down by subduction, so captured naturally by the planet, and then you know, dissolved in water, for example, carried down between continental plates, that kind of thing. That unfortunately is not going to work on Venus because it has no continental plates, because it doesn't have much magnetic field and rotation and those kinds of things. So I suppose if you could invent some kind of carbon drawdown method, and we're happy to run it for an incredible number of lifetimes, you might be able to remove that massive CO2 content. And then perhaps then the runaway greenhouse effect would correct itself in some way. To be honest, I haven't seen any discussion of that, but I have seen some discussion of whether you could turn yourself into a floating life form with some sort of dirigible in the clouds, and that, you know, ultimately astronauts could set up a cloud base rather than a surface base, which would be something pretty amazing.
So you would be orbiting around Venus rather than in Venus, because there'd be all this atmospheric pressure as well to deal with, not just the carbon dioxide.
Yes, exactly.
Exactly. Well, I think that's all the questions. Thank you very much indeed. Thank you.
Thank you. It's been a pleasure.
Well, thank you, Rona. Thanks for handling the question and answer session. That talk, Jane, fairly stimulated the questions coming out, and a whole range of them as well. Can I just take this opportunity to thank you, Jane, for a most interesting and captivating talk. Interestingly, I worked in the malting industry, making malted barley for whiskey, and we had large grain stores of barley, silos, and we used phosphine gas if we had a mite or an insect infestation, you know, to kill it. So it's interesting to see the juxtaposition where phosphine is actually an indicator of life, you know. I was also fascinated, my first degree is biochemistry, so your colleagues' biochemistry life cycle thing where phosphine is emitted was quite interesting to me, and I'm going to have another real look at that.
Well, I'm really glad there was something for everybody in there. Thank you very much for all the really advanced questions, and it was a pleasure. If anybody thinks of something else, I hope Eric might pass on an email or something. I'd be more than happy to engage in correspondence.
Well, I'll certainly do that for you, Jane. Now, pre-COVID times, you would be here with us and we'd all be applauding you and cheering you. But we can't do that because of COVID, of course. So as a token of appreciation, you'll receive a thank you card designed and printed by Pauline, but we'll need to send them to you in the old-fashioned postal way.
I look forward to that. That's most kind of you. And I do hope in a future year I might be able to come and visit. I would love to come back to Scotland and to meet you all properly.
Well, you'd be
Okay,
most
well, bye for
welcome.
now then. I will get off. Goodbye from me and the knitted Dalek in the background.
Okay, thank you very much, Jane, and hope
Thank
to
you
meet you
all.
again. And now to the club news and the Astropics for the month. Pauline is with us again this month to show you what our club, our sister clubs, and individual amateur astronomers and observers in the north have been getting up to. She's got many beautiful and interesting images to show you, but first she opens with a short educational piece for us amateurs. Over to you, Pauline.
Thank you very much, Eric. Summer is on its way and day length is increasing, but of course this also means that we've lost our proper dark sky. So I'm not going to do a constellation tonight, but instead talk very briefly about an astronomical subject that is something that we come across very often. And I've chosen magnitude tonight. And this is to do with the brightness of an object in the sky. It could be a star, planet, galaxy, or anything else. But the reason I've chosen magnitude is because it's used so often that we read about it in books and magazines, we hear about it on the television and radio and astronomy programs. And of course, I'm always talking about magnitude if I am doing a constellation. But I am very aware that there are beginners out there and that they may not have much of an idea of what magnitude really is. But those of you who do know about magnitude, well, hopefully you'll go away with something that might be new. So the magnitude scale has been around for a couple of thousand, used by Hipparchus in 129 BC. And what he did was to divide all the naked eye stars that he could see into 6 groups of different brightnesses. And he started with magnitude 1, which were the very brightest stars that he could see, all the way down to magnitude 6, which were the faintest stars he could see. And this worked well for a couple of thousand years. But then in the 19th century, a Norman Pogson decided that magnitude scale needed to go on to a precise mathematical footing. So he did this by defining a star of magnitude 1 as 100 times brighter than a star of magnitude 6. Therefore, a difference of 5 magnitudes, 1, 2, 3, 4, 5, corresponds to a brightness of 100 times. So each step of 1 magnitude is equal to a brightness difference of just over 2.5 times. It's actually 2.512 to be exact. Now it's a logarithmic scale, which means that, for instance, you don't say 2.5 times 4, because you won't end up with the answer that's close to 40. So it's 2.5 times itself plus and then times its product. And I'm sure mathematicians will be able to put that in a better way than me. But that's how you end up with these numbers. And please note that the numbers have been rounded up or rounded down as necessary. Nowadays, the brightest stars have a magnitude of 0 or a negative number. For example, Vega has a magnitude of 0.03. Sirius, which is the brightest star in the sky, therefore brighter than Vega, has a magnitude of minus 1.44. Our sun has a magnitude of minus 26.74, but then it is the brightest object in the sky. Stars fainter than a magnitude of 0 are given progressively larger positive magnitudes. So Deneb is fainter than Vega. Both Vega and Deneb are found in the summer triangle. and Deneb has a magnitude of 1.2. Miser is fainter, so it has a magnitude of 2.2, and Alcor, fainter still, has a magnitude of 4. Miser and Alcor form the pair of stars that you can see in the tail of the plough. And they can be really useful for judging the conditions of your sky. So if you can see Alcor, it means that you can see stars of at least magnitude 4. So that can be quite useful. Now, of course, we've got telescopes nowadays, so we can go even further than magnitude 6. Magnitude 6 is the faintest we can see with the naked eye from a dark sky site. But telescopes today can see all the way down to magnitude 27. And in fact, Hubble, when it did the ultra deep field, was able to see galaxies that were as faint as magnitude 31. So that is really faint. But that's not quite the end of magnitude, because there are two types. There's apparent magnitude and absolute magnitude. Now, apparent magnitude is the one we use all the time. That's the one we find in books, magazines, and that's the one, of course, I give you when doing a constellation. And this is the apparent brightness of a star as seen from the Earth. So it depends on the distance of that star and also the amount of light or energy that it produces. So for example, if we've got a very bright star that's a long way away, we might find that this star is actually brighter than a star that is much closer to Earth, but is actually dimmer. So that's what we go on. We go on the apparent brightness of these stars, whatever the distance. Absolute magnitude, on the other hand, is the true brightness or intrinsic brightness of a star. And it's the apparent magnitude that a star would have if it were at a distance of 10 parsecs or 32.5 light years. So what you're doing is putting all the stars onto a level playing field so that you can compare their brightnesses. So basically you're taking stars from maybe quite a distance and you're putting them at 10 parsecs. And that's the same with all the stars. If we take the summer triangle as an example, you'll see that Vega in Lyra, we know it's 0.03, its apparent magnitude. But if we have a look at its absolute magnitude, you'll see that it's actually fainter than the apparent magnitude. So why would that be? Well, that's because it's closer to us at 25 light years than this level playing field, which would be your 10 parsecs or 32.5 light years. So in effect, we've taken Vega and we've moved it away from the Earth. So of course it's going to be a little bit fainter. And it's the same with Altair in Aquila. And if you look at the distance, 17 light years, well, that's really very close. Move it back, and that's why you have an absolute magnitude of 2.2. If you take the sun, our sun, remember it's got an apparent magnitude of minus 26.74. So, and it's, of course, it's very close to the Earth. Now, if you move it back to our level playing field, our 10 parsec or 32.5 light year distance, it's going to be a lot fainter. In fact, it's only something like 4.8. So that's what its absolute magnitude would be. So the reason these two stars are so bright is because they are near, same as our sun. But Vega, although Vega and Altair are relatively ordinary stars, Vega is a blue star, so it's hot and bright. Altair is a white star, not quite as hot and bright. Our star is a yellow star, and again, it's not as hot and bright as these two stars. Now, if we look at Deneb, again, it's a bright star, but it's not quite as bright as Vega and Altair. It's 1.2. But look at the distance. It's 3,200 light years away. So you take that star and you put it on our absolute magnitude scale, our 10 parsec or 32.5 light year distance, and you'll see it has an absolute magnitude of -8.7. So what we're doing here is comparing the brightnesses of all the stars. But it's apparent magnitude that's the one you need to know about. That's the one that you will read about, you will hear about, unless you're doing an astrophysics course or something when you will learn about absolute magnitude. So if we now have a look at what's up in the sky, we have the new moon on the 11th of May, full moon on the 26th of May, and the full moon is a supermoon this month, so it appears bigger because it is closer to us in its orbit. And there's a lunar eclipse, but unfortunately, you can see where we are in white, that means it's daytime. So you would need to be in Australia or New Zealand, but I bet that's a really cool lunar eclipse this time. So what else can you look for? Well, of course, I've been talking about summer triangle. We've got Vega and Deneb, which are circumpolar stars. That means we see them all night and all year. Altair, however, will disappear over the winter, becoming noticeable again late evening this month. So it's really after this month that we begin to see the summer triangle in all its glory. So let's just have a look at these stars being circumpolar. When I moved to my current house just over 10 years ago, I got a wonderful northern horizon. And I used to watch two bright stars over the winter, just skimming the edge of the northern horizon. And it took me a little while to work out what they were. And of course, they are Vega and Deneb. So if you watch the blue arrow with Vega, and this is November, December, January, February, March. So you can see how it just skims along. But at our latitude, it means that we can see it all year, all night. And again, with Deneb. So with Lyra, we have also got Arcturus in the sky, which will be noticeable. Arcturus is the fourth brightest star in the sky, Vega the fifth, and then Capella is the sixth brightest star. So as well as the summer triangle, we've got these other bright stars that you'll be able to see, even though it's going to get lighter and lighter at night. But Capella is interesting. We think of Capella and its constellation of Auriga as a winter constellation, and it is, but Capella is also circumpolar. So it will dip down a bit and then start coming back up again. And if you see noctilucent clouds, then very often the bright star within them is Capella, because Capella tends to be in the northeast during the summer months. And noctilucent clouds should start appearing from around the third week in May to perhaps the first week in August. These are our highest clouds. They're found in the mesosphere, 80 to 85 kilometers up. And they're made up of tiny, tiny ice crystals that have condensed around space dust. These are the meteoric tiny fragments from meteors. And of course, they have this glorious blue, electric blue color, often with the whitish, gray, silvery filaments beneath it. And at this time of year, certainly in midsummer, we'll see this perpetual sunset into sunrise along the northern horizon when you're hopefully looking at noctilucent clouds. I find that 1 o'clock in the morning on a July morning tends to be quite a good time to see noctilucent clouds, but as long as the sun has set and it's between 6 and 12 degrees below the horizon, that's a possible time to see them. We also have 3 planets in the evening sky. Unfortunately, you need a clear northwestern horizon. Mercury is really tricky to see because, of course, the twilight. But although Mercury starts bright, magnitude -1.1, you won't see it so low down. As it climbs higher, it will also become fainter. By May the 13th, when you've also got a crescent moon close by, Mercury has a magnitude of 0.1. But this is about the best time to see it. And I found a really good website with a little calculator that tells you what time of night from our latitude it's worth looking for the planets. So Mercury on May the 13th will be about 25 to 11, or 20 to 11. So that's the time to look for it. By the time Mercury gets right to its highest point, which isn't much more than this, it's too faint to see. Venus, again, difficult to see initially. It's very low down, but it's incredibly bright, -3.9. So it's worth looking for after sunset, but wait a little bit, wait until the 2nd or 3rd week in the month of May. By the end of May, it's worth looking at 25 to 11 in order to find Venus. And then Mars is also visible. It's dropped of magnitude 1.6, but it's in a darker part of the sky. And certainly the first couple of weeks in May, you should be able to see it. The crescent moon on the 15th will guide you to it. And you may well also be able to see it when there's a crescent moon on the 16th. And if you're desperate to see Jupiter and Saturn, well, if you get up really early in the morning, 4 o'clock for Jupiter, 3 o'clock for Saturn, they are better placed and easier to see because they're out of the twilight. Jupiter shines at magnitude -2.5, so should be easy enough to see. Saturn is 0.6, bright enough as long as the sky is still dark, but don't bother looking at the end of May because the moon will drown Saturn out. Now, this is a video of Ingenuity, the helicopter on Mars, and it's absolutely astonishing. I mean, what an incredible feat. This is the 3rd flight. The first couple were just getting it off the ground and landing again safely. This one, you can see it's flown 50 meters, so it's now out of the shot. But it's going to be so useful finding the best route for Perseverance to follow when it finally goes north to look for the delta. But in the meantime, it'll be flying around looking for the best places, the best rocks for Perseverance to do its scientific studies with. The 5th flight that Ingenuity will be taking, it will take off, go up, go across, and then it's going to land where it ends up. So that will be a good chance to see how well they're able to control it when it's out of sight. In the meantime, Perseverance has had a little bit of a rest, making sure that everything is working perfectly, but it is now beginning to look for objects to do its scientific studies. So, club news. Well, as Eric has already pointed out, we have the webinar and it's working beautifully. So very well done, everyone. It's our very own webinar now. We've bought it and at a cheaper price because we are a charity. So there are some good things about being a charity. And thank you to Lisa and Matt for volunteering to help with the webinar. They, plus Eric and Dave, have been working really hard getting it up and running. It's been a steep learning curve. Now, as for the website, we would still appreciate help if you've got a spare even 10 minutes or so. That would be great. And for membership subscriptions, if you could pay as soon as possible, we would be grateful because this would really help us with our finances. So thank you. And live observing webcasts have been lacking. We send our apologies, but this is due to all the time that Eric and Dave have had to take in order to get the Zoom webinar up and running. It's been very hard work learning how to produce it and to deliver it, but they've done extremely well. And as for our observatory, now we have been checking it to make sure all is well. On the last visit, we discovered a couple of problems. Now the telescope has not been used since October, and it wasn't terribly happy about waking up. So the electrical contacts were cleaned and it's now working again. And you can see the cupboard just behind the telescope. This is a photograph taken by Dave, which is full of electrical wiring. This is where the contacts had to be cleaned. Unfortunately, it tends to get a lot of moisture, so Eric took the door home and put in a couple of vents, so that should make a difference. There's also been a water leak outside the observatory. Now, Jimmy, the handyman, who has been at Culloden Battlefield for 35 years, and he is almost 70, can turn his hand to absolutely anything. So he has said he's going to try and fix it. I've not heard anything back yet, so fingers crossed that he manages. In addition, we need to get the biosystem, which includes the septic tank, serviced. Again, this is in hand, although I've not heard back from the chap yet recently. And then, as you probably know, and this has been ongoing for a while, the path to the observatory is pretty awful when it rains. There are potholes which fill with water. It gets incredibly muddy. It's horrible. And last year, we had arranged a meeting with the Culloden Battlefield manager just as lockdown started, so we couldn't do it. However, I have actually spoken to the manager, and he has said, well, they have now received funding to resurface their car park, to make an overflow car park, and there should be money to refit our path. So I am 99% certain that means that they will do it free of charge, which will be fantastic. Okay, now here we have your wonderful photographs, and we start off with Dave's photograph of a night sky. So there is Cassiopeia. And he entitles this one The Seven Sisters, because that's where the Pleiades are. But what a beautiful sky, not quite dark, but full of stars. And there we have it again. So now this one is entitled Arthur Weasley's Flying Anglia. And if you don't read the Harry Potter novels, you won't have a clue what we're on about. So I'll give you a heads up. It's in the second book, which is a Chamber of Secrets, where Harry and Ron drive their father's car, which just happens to fly. And of course, in the films, there is the wonderful viaduct. It's not this one, but there is one. So that's why it was named as it was. And here's a wide angle, well, a wider angle picture of this fantastic viaduct and glorious sky. Now, Eric took part in North Ronaldsay Science Festival. I think it must have been in March. And this was his reward. This is the all-sky camera that Eric runs, and this is called a kilogram, and it shows you now I forgot to ask you, Eric, how often a picture is taken, but as you can see, this particular night was completely cloudless. And then we go into morning sky once again. And in fact, this is the same night. I'm pretty sure we woke up, or after 6 o'clock, it became misty, but the night was glorious. And here is Henrietta back again. So just when we thought she had disappeared and gone away, that's certainly not the case. And we've got some wonderful star trails captured by the All-Star camera. If you have a look at this here, there are a few what looks like meteors. Could be some over here too. One there. But this one in particular, Eric has taken this particular frame and you can see the meteor here. And Dave has managed to capture a meteor and it's got some colour in it. So this is quite an interesting one. And here we have some of his moon photographs of a full moon rising at this particular through the trees, which is absolutely beautiful. And this is quite an incredible photograph. Now, new moon was the 12th. So this was the day after new moon. So Dave has captured just about the thinnest moon that is possible. He uses a towel reflector with his Nikon camera. But this particular photograph was taken by Sue Shackleton of North Ronaldsay, and she has captured earthshine absolutely perfectly with the bright moon on the other side. And you have to overexpose the photograph in order to get moonshine, earthshine, which is what you can see here. So that the moon itself is not in focus. But if you do focus it, then you lose the earthshine. But this is a beautifully focused moon. And here it is again, same night, and taken, as I said, through his towel. Now, we're increasing the moon in size. I love this photograph. It's really atmospheric with looking at it through the clouds. This is the moon on the same night, which is why I have put them both together. And this one, here we have Mars, but Dave tells me it's actually a composite. So both were taken at different times and then put together. But the moon itself is beautifully in focus, and this one is increased in size. And we're getting bigger and bigger. And here we have a wonderful view of the moon with the crater Theophilus. And this particular image of the moon shows these Macrae really quite nicely. So we've got 4 Macrae there. This is the Imbrium Basin, and this crater here is Copernicus with its 2 central peaks. This is a very close-up photograph. Dave has entitled it Looking for Footprints, and my goodness me, I think we can almost see them. But what's really interesting is the relief that you can see in these photographs. It just shows you how high some of these crater walls are. Extraordinary. And here we have Clavius, which in fact you did see in the previous photograph, and the crater Tycho. And this is a wonderful photograph of a moon halo. And this was taken on the 25th of April. And Matt captured the moon halo on the same night. Right, so that's the moon. And now we're going to have a look at some sun photographs. This is Eric's sun setup. So we have a 60mm guide scope. And this one has a white light filter on it. So this gives you your white lightest photographs, a term coined by Anthony. And it has a monochrom camera attached to it. And then we have Eric's hydrogen alpha telescope, which is a Lunt. And what he will do, or what he has done, is to take this special astrocam from the main telescope, and he will have fixed it to the Lunt in order to take the photographs that you'll see. But I also notice, Eric, you're going to need to do a bit of dusting. Look, you're not going to talk to me again, are you? And this is a hydrogen alpha photograph taken by Eric. So we're looking at the chromosphere. That's the lower part of the atmosphere above the surface of the sun. And you can see 3 sunspots. And our sunspots don't look never quite look as well as they do in white light, but you can see them then. You can see a lot of structure with them. So we're looking at the middle one. This is sunspot group 2816. And there it is again. And the reason we've got different colors, Eric says, is because of the different way of processing these images. And this is sunspot group 2817. That was on the lower left-hand edge. And this is the upper right-hand edge, sunspot group 2818. What you can see here, these black streaks, they're known as filaments. And these are clouds of gas that are suspended in the atmosphere of the sun by powerful magnetic fields. They appear dark because they are cooler than the rest of the gas beneath. But these filaments are also prominences. So if you see those filaments on the edge of the sun, then we call them prominences. And this is an absolutely beautiful set of prominences. And in fact, close-up picture shows you the prominences again. This is known as a hedge prominence. And the detail is amazing. But look at this. This is incredible detail. And again, been processed differently. But because we're looking at it so closely, you can see other tiny little prominences at the edge here. And this is Dave's sun setup. So this is the TAL telescope, and it has got a white light filter on it. So it's 150 millimeters. And he attaches his camera, which is a Nikon, a D700 Nikon to it. So this is a white light image, or white lightest. And this is sunspot group AR282814, which you can see just here. And this is the same sunspot group that Eric had in the middle of his image. So that's 2816. And what Dave has done here, he's called it white lighter solar rotation. Maybe that should be white lightest solar rotation. He's tipped this up so that these sunspot groups are in the same relative position, because it depends on which way you have the eyepiece and therefore the camera as to which views you end up with the sunspots on the sun. But this is taken on the 21st of April, and this one the next day, and you can see how far the sunspot groups have moved already in that day. I love this photograph. Another stormy looking picture, very atmospheric, with the clouds coming across the sun, and you've got all three sunspot groups. I picked out 2816, which is this one, but they're actually all there. And this is my attempt, and you'll see again, these are the same sunspot groups, but in a slightly different orientation to Dave's. So this middle group here is this one here. It's just really difficult trying to get the absolute focus right. And then there have been a series of sundogs. I haven't seen them for years, and all of a sudden I saw three of them. So there's a sundog just there. And with this image, it's a very subtle sun pillar. You almost have to use averted vision. Well, you do have to use averted vision in order to be able to see it. It is there. And then Gwen has got a really superb sundog. So you can see the rainbow colors in it, how the sun's light is refracting through ice crystals and giving this wonderful picture, this rainbowish image. And it always occurs at a particular distance away from the sun. And then this picture, this is another sundog, but somebody pointed out to me, oh, look, there's a halo. And indeed, it's part of a sun halo, not there completely, again, extremely subtle. And now we have some deep sky photographs. So this is one by Dave Horsehead Nebula with the Flame Nebula. And you can see the Horsehead beautifully here. And this is the Flame Nebula. This is the Leo triplet, these 3 galaxies in Leo here. M3, globular cluster. M51 is a spiral galaxy in Canis Venata C. You can see the spirals. And this is the little galaxy that's close to it that interacts with the main part. So this is a larger image taken by Eric, but the opposite way round to the one that Dave took. And this is a single frame. So once he's processed it, this is going to be a fantastic image. And the same with this. This is M81 in Ursa Major. Absolutely fabulous spiral galaxy. Picked it up really well in this image. And then we've got M94, spiral galaxy in Canis Venata C. M101, and you can really see, well, I should do it this way, the spiral in this particular galaxy. And here is the spindle galaxy, M102. It's a lenticular galaxy, which means it looks like an edge on the spiral, but it's not a true spiral galaxy. And I'll show you what it should look like, because it's very, very faint. Now, Dave uses his, get this right, a 300mm lens with his Nikon camera in order to capture these particular photographs. So again, another spiral galaxy, M106 in Canis Venata C. And now he's taken a number of galaxies. Now I could get you to actually have a look and see how many galaxies you can count. But fortunately, Dave has labeled them all for us. So there are quite a few here. And here is an edge-on spiral. I don't know what they're called, but this is what the spindle galaxy looks like. It's just that the proper spindle galaxy is just too far away for Dave's image setup to actually capture like this. But this is a wonderful galaxy here. And here we've got another one. And this is the Rossetti Nebula. Now, last month I showed 2 of them Dave showed 2 of them by Mark, using different filters. But when he puts the filters together, he gets something like this, which is absolutely beautiful. So well done, Mark. And now my favorite section, the aurora. So this is a low-level aurora by Lisa, who is working hard on the webinar tonight, along with Matt. And you can see this gorgeous color in the sky, and we've even got the Milky Way. So low-level aurora still with, looks like meteor and perhaps, or maybe both are satellite trails. And this one is the aurora from the all-sky camera. And if you look at on the northern side, you can just about make out the aurora and some nice dancing rays. So if you look again, there they are. Beautiful. So that is what Lisa has captured here. This was on the 15th. And Sue also captured the aurora. Looks slightly better, but then she is further north. So I would expect it to be, when I say better, I mean brighter. And it's beautiful with all those rays, absolutely gorgeous. And then Mick from Sigma captured a series of pictures of the aurora, all on the same night. And these are just stunning. Colors, rays coming up from the archway. And then we have Nora Watson, who's photographed the aurora over Cromarty on the 20th. So there's been quite a bit of aurora around, although sadly I haven't seen any. So thank you very much, everyone. Please join us at the Zoom after meeting chat. And as Eric said, the link is in Monday's email, but it'll also be in the chat box. So thank you very much for your continued support.
Pauline, thank you so very much for that. That was just fabulous. I'm going to get the duster out now that I've been found out. Also, unfortunately, I'm at an age that my unaided eyes can no longer see a magnitude 6 star, even in a perfect sky.
Same here.
I saw you've pointed out some planets for our resident night owl Dave Davidson to photograph this month. And
well, he can try.
Yeah. Well, he'll try. I'm sure he'll get them.
Yeah, they're not easy to see, but Dave, if anyone's going to get them, I'm sure Dave will.
Absolutely. I can hardly believe the amount and the variety of images we've received over the past month. It's just great that so many of our members and followers are active observers.
Yeah.
Just thank you to all the contributors in all our astronomy clubs and groups across the north of Scotland, and for your permission to let us show your work. Well, that's just about us for tonight. I want to thank our technical support team, the Haas Tech team, as we call ourselves, of Lisa Pattenden and Matt Lafferty, for working so hard and so well in the background tonight. I can tell you we have been chatting to each other via WhatsApp. Also unknown to you all, Rich and Mick from Sigma, they were loitering in the wings just in case something fell over. But thankfully it didn't, and everything was all right on the night. Now, the night may be finished for some of you, but if you want to join us for a wee informal blether, please click on the link, which should be showing in the chat box. If not, it's in the email you received from Rona notifying you of tonight's events. Clicked on the link, you'll see a screen or a box telling you that the meeting is yet to start, and it will take a couple of minutes for me and Lisa to close down this meeting and open the next chat room. So just hang about, make a cuppa or pour yourself a glass until it does open. Anyway, to all of you, thanks once again for coming along. Until next time, clear skies and keep looking up.